Hello, friends and colleagues. Ryan Castillo here, Managing Director at Adamas Intelligence. Today I'll be speaking to you about the outlook for electric vehicles, the traction motors that move them, and I'll walk through some of the key considerations that an automotive OEM faces when choosing a motor type for their next generation of electric vehicles. Before I do, however, please note that this video will contain forward-looking statements related to future events that are not necessarily certain, so please do keep that in mind. All right, on the agenda today, I'll start off with a review of how the EV and motor markets have evolved in recent years, zooming in on the competitive landscape of different motor types in use today. We'll then explore some of the key considerations that an OEM faces when deciding what motor or motor types to go with in their future EV models. Considerations related to technology, cost, the environment, and the supply chains they source from. With these considerations in mind, we'll take a look at what the outlook holds for global EV and motor markets before wrapping up with a summary of key takeaways and a few more words about us, Adamas Intelligence. On we go with a review of global EV and motor markets. Since 2015, and since 2020 specifically, global EV sales have been growing aggressively fast. In the face of the pandemic, in the face of persistent supply chain challenges, in the face of Russia's invasion of Ukraine, and in the face of the economic headwinds born out of all of these challenges, the market has sprinted ahead. It's that resilience, that unstoppable growth, that commitment to overthrowing the old in favor of the new that makes this shift to electric mobility a revolution, an electric vehicle revolution. And frankly, I think that's a big reason why a lot of people are watching this video today, because this shift, this revolution, presents generational opportunities, but also brings to bear unprecedented challenges. As shown on the left, since 2020, global passenger EV sales have grown at a compound annual growth rate of 61%, nearly tripling in just 2 years and showing little signs of slowing down in 2023 year to date. This growth has been driven mainly by China, followed by Europe, followed by the US, and in terms of EV types, as we can see in this chart on the right, has been led primarily by battery electric vehicles and plug-in hybrid electric vehicles, and to a lesser extent, conventional hybrid electric vehicles, which is good news if you're a rare earth or magnet supplier, given that the former two EV types tend to use more powerful motors and generators than conventional hybrid electric vehicles, translating into greater magnet use per EV on average. At a high level, there are 3 types of EV traction motors in commercial use today. We have permanent magnet motors, including permanent magnet synchronous motors and permanent magnet assisted synchronous reluctance motors. We have induction motors, and we have electrically excited synchronous motors. Of these 3 motor types, only the permanent magnet motors contain rare earth permanent magnets. Over 90% of all passenger EVs produced globally to date contain one or more permanent magnet traction motor. And this trend continues to hold despite some OEMs opting for alternative motor types for main or auxiliary drives in recent years. As we can see in the chart on the left, in 2022, 97% of all passenger EVs sold globally, including hybrid, plug-in hybrid, and battery electric vehicles, used a permanent magnet traction motor. This proportion was trending down in the middle of the last decade when Tesla used induction motors only, but has since rebounded following Tesla's switch to permanent magnet motors for its main drive. On top of aggressive EV sales growth and the high penetration of permanent magnet motors, we also continue to see an increasing percentage of EVs sold each year containing more than one traction motor, as indicated by the blue line in the chart on the left. And consequently, we see the average motor power per EV rising alongside, translating into an increase in rare earth magnet loading per EV on average. And this is also good news if you're a rare earth or magnet supplier. But what if you're an OEM making electric vehicles or making motors? What are some of the key considerations you may be facing as you design and plan your motor strategy going forward? Well, in terms of technology, there are a lot of moving pieces to consider. The OEM of yesteryear, today, and tomorrow must take into account many different factors when choosing an EV traction motor. There is no ideal motor for every situation. Each motor, as part of a broader drivetrain system, must be designed for the host vehicle's specific requirements, with key considerations being performance, efficiency, motor cost, inverter cost, robustness, overload, stall torque, manufacturing, noise, vibration and harshness, recyclability, power at max speed, and many others. An OEM must also take into account customer expectations. Do they want fast acceleration, strong off-roading capabilities? Will they be driving at high speeds for extended periods? An OEM must also consider the scalability of each architecture and associated demand volumes. Do they justify investing in new plants and assembly lines? And an OEM must also consider the current and future expected state of supply chains and supplier capabilities. Is the supply side robust, resilient, transparent? Are prices stable or volatile? And finally, an OEM must also consider the environmental, social, and governance-related aspects of the supply chains they source from and the products they deliver to customers. In terms of the motor technology options available to EV makers going forward, there are 5 main flavors, 4 of which I've already touched on, plus a variety of sub-flavors that I won't go into today. From left to right, we have permanent magnet synchronous motors, shown here as PM. We have permanent magnet assisted synchronous reluctance motors, shown here as PM-SR. We have induction motors, shown here as IM. And we have electrically excited synchronous motors, shown here as EESM. Synchronous reluctance motors are also an option available to the auto industry, albeit one that we currently don't see used unless permanent magnet assisted. As we saw earlier, permanent magnet motors dominate the EV market, with an 89% share by motor power deployed as of April 2023. Followed by induction motors with 7% of the market and electrically excited synchronous motors with 4%. So why do some OEMs use one type of motor over another? And why do some OEMs use multiple motor types? Well, it's because each motor type has different characteristics, different strengths and weaknesses that determine its suitability for the type of vehicle in question, the type of drivetrain being designed, and the expected driver behavior. A permanent magnet synchronous motor, for example, is known for its high performance and efficiency, particularly at lower speeds, but is also the most expensive technology option available. A permanent magnet assisted synchronous reluctance motor, on the other hand, couples the high performance and efficiency of a permanent magnet synchronous motor with the robustness and power at max speed of a synchronous reluctance motor to offer the best of both worlds. An induction motor, while low cost, resistant to overload, and offering good stall torque, suffers on the performance and efficiency front. And similarly, an electrically excited synchronous motor is typically low cost and has slightly lower performance and efficiency than a permanent magnet synchronous motor under low speed conditions, but offers excellent power and efficiency at high speeds, making it well suited for certain applications. On the right, we've overlaid each motor type in comparison, showing their relative strengths and weaknesses. As we can see, for performance, efficiency, and robustness, permanent magnet motors shine. For stall torque and overload, both important considerations for off-road vehicles, induction motors are well suited. And for low cost and high power and efficiency at max speeds, electrically excited synchronous motors stand apart, making them an excellent auxiliary motor if paired with a permanent magnet main motor in our view. All right, so with technology behind us, excuse me, let's explore some key considerations that an OEM faces in more detail. In general, permanent magnet motors offer the best cost-performance balance for most applications. And in our view, cost-performance balance is what defines the ideal motor for a given application. As we can see in this chart, a permanent magnet motor is the lightest, most power-dense motor type available, followed by electrically excited synchronous motors and induction motors, an important design consideration from the standpoint of an electric vehicle manufacturer. However, despite being the lightest, the bill of active materials for a permanent magnet motor is roughly double that of a comparable electrically excited synchronous motor and 35 to 50% higher than a comparable induction motor, entirely because of the relatively expensive permanent magnets that this motor type contains, which on its own is a very important consideration for the cost-sensitive auto industry. But if we recall that the efficiency of each motor type differs and that permanent magnet motors are the most efficient motors for most driving applications, then we can quantify the value of battery cost savings enabled by this motor efficiency at the level of the powertrain, as shown in the table in the middle on the right. Therefore, if the increased efficiency of a permanent magnet motor enables battery thrifting of just 1 kilowatt hour, that savings is worth around $100. If 2.5 kilowatt hours, that savings is around $250, which is more than the value of permanent magnets in the average motor. And if saving 5 kilowatt hours, that's worth around $500, which pays for the entire permanent magnet motor's active bill of materials. Shown in the bottom left corner in yellow is the added battery cost an OEM could expect if using an induction motor or electrically excited synchronous motor and trying to match the driving range of a comparable permanent magnet synchronous motor. For a 60 kilowatt hour battery electric vehicle, analogous to an entry-level Tesla Model 3, the added cost at the drivetrain system level makes an induction motor far more expensive, and an electrically excited synchronous motor of comparable cost, albeit the latter motor type has slip rings that require periodic replacement during its operating life, which adds additional costs over and above what is being shown here. Similarly, for a 100 kilowatt hour battery electric vehicle, analogous to a performance or long-range electric vehicle variant, the added cost at the drivetrain system level makes an induction motor far more expensive than a comparable permanent magnet motor, and an electrically excited synchronous motor slightly more expensive, albeit especially so when considering the cost of periodic slip ring replacement. So a lot of food for thought so far. Number one, OEMs have a variety of technology options to choose from. Number two, the cost-performance balance is what defines the ideal motor because it's what determines overall drivetrain system costs. And number three, as we'll see, on the environmental front, an OEM must consider these technologies, costs, performance, and other metrics in the context of their associated environmental footprint. Why? Because having the cheapest, most efficient, most robust motor is all for naught if it is also the most impactful, environmentally speaking. As you might be aware, the manufacturing footprint of an electric vehicle is roughly double that of a comparable internal combustion vehicle. So why do people buy them? And why do climate-concerned people promote them? Well, it's because over the operating life of an electric vehicle, including the manufacturing stage, an electric vehicle will have far less environmental impact than a combustion vehicle, and that's what matters most. And the same can be said for electric vehicle traction motors. A permanent magnet traction motor made using raw materials will almost always have a greater environmental footprint upfront during manufacturing than alternative motor types that don't contain permanent magnets. But studies have shown that the manufacturing of an EV motor makes up just 1 to 2% of its lifetime environmental impacts. And using that motor, running that motor, operating that motor makes up 98 to 99% of its lifetime environmental impacts. So if you want a motor with the lowest environmental impact, the operating efficiency of that motor is 100 times more important than its footprint up front during manufacturing. And that is where permanent magnet motors shine. As we can see in the charts on the right, we can see the lifetime gross energy requirements on the top and the global warming potential on the bottom of each motor type, including that manufacturing stage. And we can see that in this case, the permanent magnet assisted synchronous reluctance motor performs better than incumbents. Lastly, aside from technology, cost, and the environment, an OEM must also take into account the nature of the supply chains from which they source. Are they resilient, robust, transparent, and predictable? In terms of the global rare earth permanent magnet industry, we can see in this chart that supply at each step of the mine to magnet value chain is dominated by a single source, which presents a significant risk to those reliant on this supply chain, a risk that could outweigh the technology, cost, and environmental considerations reviewed earlier, and a risk that may underpin the reason why some OEMs have adopted alternative motor types in recent years. We're currently seeing unprecedented efforts in the US and Europe to develop alternative mine-to-magnet supply chains, often closer to home. But the sheer speed at which demand is growing means that these initiatives were behind before they even started. Another concern and consideration is the predictability and stability of rare earth prices, which have been both unstable and unpredictable since 2020, leaving many OEMs wondering what the future holds. Due to these concerns, we expect that OEMs will increasingly focus on modular EV designs going forward that allow them to plug and play different motor types if required or desired. Looking ahead, we forecast that global passenger EV sales will rise at a compound annual growth rate of 10.8%, from around 14.5 million vehicles last year to slightly more than 91 million vehicles in 2040, led by especially strong uptake of battery electric vehicles. Taking into account all that I've discussed today, coupled with our views on rare earth supply, demand, and prices, we project that just around 73% of all passenger EVs sold globally in 2040 will use a permanent magnet motor containing rare earth permanent magnets, down from around 97% last year, as alternative motor and magnet types such as electrically excited synchronous motors and ferrite magnets capture market share and benefit from what we expect will be limited global availability of rare earth magnets. We also expect that an increasing number of OEMs in the years ahead will embrace multi-motor powertrains that pair different motor types together to leverage respective strengths and offset respective weaknesses. The Tesla Model 3, for example, is an EV that uses a permanent magnet-assisted synchronous reluctance motor as the main motor to maximize efficiency at low speed, and an induction motor as an auxiliary motor to maximize efficiency at high speed and minimize magnetic drag. I'll take a moment now to summarize some of the key takeaways from the presentation. OEMs must take into account many different factors when choosing an EV traction motor. There is no ideal motor for every situation. Each motor, as part of a broader drivetrain system, must be designed for the host vehicle's specific requirements. In general, permanent magnet motors offer the best cost-performance balance for most applications, and in our view, cost-performance balance is what defines the ideal motor for a given application. For lowest environmental impact, the operating efficiency of a motor is 100 times more important than its upfront environmental footprint during manufacturing, and operating efficiency is where permanent magnet motors shine. However, perceived supply chain risks could outweigh technology, cost, and environmental considerations, potentially underpinning why some OEMs have switched to alternative motor types in recent years. And towards that end, mine-to-magnet supply chain diversification is underway, but the sheer speed at which demand is growing means that these initiatives were behind before they even started. Downstream capacity must now race to catch up to ensure that the outputs of tomorrow's new mines can be converted into the magnets that OEMs need. And lastly, as you may be aware, Adamas Intelligence is an independent market research and advisory firm focused on mine-to-application supply chains for critical metals, minerals, and materials. Founded in 2012, we count clients on 6 continents, including exploration and mining companies, institutional investors, technology and materials developers, government agencies, as well as other advisory firms. Thank you so much for tuning in today. We look forward to being in touch.